talk today about scientific notation and metric prefixes. Previously, we looked at this YouTube video where we looked at the scale of the universe from our perspective, basically, as humans here on Earth. So when we were looking at that, right now we can see the 1 meter. That's the circle of objects in the middle. What if we were to describe the size of, say, DNA? We'd have to say 0.00000000000 maybe meters. Okay, if I did those zeros correctly. That's a lot of different zeros to say before explaining what the number is. So because we're scientists, we can come up with what's called metric prefixes to help describe these numbers to prevent us from having to write all those zeros. Okay, and we do it in scientific notation. Okay, so those are kind of our two buzzwords for today. Is we have metric prefixes and we have our scientific notation. The idea that you can represent zeros in what's called an exponential form. All right, so let's look at these metric prefixes. What we can see here is we've got our decimal, and we also have our exponential form. Okay. Then we have in our example where we've got the top one says 1 terameter equals 1 trillion meters. That tera is our prefix. Okay, so the tera is the prefix, same way as giga, mega, all of those things. Those are all your prefixes. Okay, the meter is simply a placeholder. All right. Meter can be replaced with any other base word. So you can have byte, like kilobyte or gigabyte, okay? Or even now we're doing terabyte gigs, right? Those are the fun ones to own, okay? In science, we also use grams, joules, liters, okay? These are all just units of measure, okay? But they are base words, okay? So whenever I'm saying megameter, I can replace the meter part with a liter, and it means, you know, a similar scale of measurement. All right. A decimal equivalent and our exponential form. Okay. Those are the two ways of saying the same thing. Okay. 10 to the 12th, an exponential form, can be represented as 1 with, count them, 3, 6, 9, 12 zeros after it. Okay. Whereas our terameter, the word tera, that literally means what you see here in the decimal equivalent, okay? A trillion, okay? Whereas if you look at, say, a deci, deci is the same thing as a tenth, okay? Or you can form deci is the same thing as here, okay? So whenever you were to write 1 decimeter, that's the same thing as putting, instead of you're having a D, deci, you can simply put 0.1 and for deci, and it's 1 decimeter equals 0.1 meters. Okay. Or if you do a millimeter, 1 millimeter is the exact same thing as saying 0.01 meters, okay? Or you can replace the prefix with its decimal equivalents, okay? All of these are just to be used in reference to. You'll be able to use this table a lot this term, okay? And so it's going to help you convert between a terameter, a gigameter, a megameter, all the way down to a picometer. Right? And remember, the point of using these prefixes is to prevent you from having to write out all of these decimal places and all of these zeros. Okay? It's a way that scientists can talk about units in a much more efficient manner. Okay? Here is literally how they get from the decimal notation over here to these exponential notations over here. 10 to the 6th literally means 10 times 10 times 10 times 10 times 10 times 10. 6 tens multiplied all together gives you 10 to the 6th. Okay? 1 is the same thing as 10 to the 0. Okay? Now, what is 0.1? 0.1 is 1 divided by 10. And 1 over 10 is the same thing as 10 to the minus 1. Whereas 10 to the minus 2 is 1 over 10 to the 2nd. Okay, that equals 10 to the minus 2, which is the same thing as saying 1 over 10 times 10. Okay? Because 10 to the second is 10 times 10. So 1 to the negative 2 power is the same thing as saying 1 divided by 10 to the second, which is 1 over 10 times 10. Okay? All right. So the whole point of scientific notation is to report a number so that only your significant digits are showing and so that every significant digit is showing. Okay? So if you leave any significant digits out, you haven't reported it properly. If you add extra digits, you have not recorded it properly. Okay? Within that scientific notation, you always have a coefficient, which is the number that goes before the multiplication sign. Then you have a base, which we always use base 10. And then you have an exponent. Okay? These are the main parts of scientific notation. Notice you will only ever have one number to the left of the decimal. Okay? And that is a non-zero number to the left of the decimal. If you were to have 0.003 times 10 to the third, that's incorrect because you don't have a non-zero number to the left of the decimal. Okay? Or if you have 62.1 times 10 to the fifth, that is incorrect because you have two numbers to the left of the decimal. Okay. All right, so when we look at our numbers, if you have a positive exponent, it should get and correspond with a large decimal number. Okay, so notice up here, we've got 65 million. Okay, so whenever we represent 65 million, what you do is you take your decimal point and you move it to the left 1, 2, 3, 4, 5, 6, 7 times. Okay, since it got moved 7 times, that number becomes your exponent. Okay, then your number, your 65, notice we only have one number to the left of the decimal. Okay, notice since we went to the left, it's positive. Okay, if we go to the right, our numbers are negative. Okay, and if that corresponds to a small number. So notice 0.0000987 is a really small number. Okay, so whenever you move this decimal, you moved it to the right, and it is a negative exponent. 4, 5. Okay, notice I stopped right here. Why did I stop right there? Because I only want one number to the left of the decimal. Okay, so that's why I stopped right there. So I have 9.87 times 10 to the negative fifth. The negative comes from the fact that I went to the right, or that I became a smaller number. Okay, and it's 5 because I moved the decimal 5 places. All right, I'll take a moment here, kind of a side note, to talk about your calculators. Okay, really recommend for students is to use this EE button on your calculator. It can look a couple different ways, but the reason I recommend it is because if you don't use your parentheses properly, when we get to more complicated mathematics down the road, you might end up entering it into your calculator incorrectly. Meaning, if you do 3.57 times 10 to the 7th times 2.75 times 10 to the 3rd over 3.1 times 10 to the 2nd. If you don't put parentheses around that bottom number, then what your calculator might do is it might take the top two numbers and multiply them together, and then it might divide them by 3.1, but then it might multiply that answer by 10 to the 2nd. Whereas you want 10 to the 2nd to be on the bottom. You want that top number to be divided by 10 to the 2nd. Okay? So what I recommend doing is if you use this E button, where it has your number, where 3.57 looks like this in your calculator. Okay? If you use that E button, then you don't have to worry about parentheses. So my suggestion to you is to either use the E button or use parentheses wisely. Okay? Get to know your calculator this semester. It will be your friend. Other examples are here, where that's a little bit off on the circle I drew. So that EE button is here. Okay? So that's another example of a non-graphing calculator. Or if you're using the calculator that's built in to most operating systems, it's this exponent button. So if you type in 1.57 and then you hit the exponent button, it'll show up as E plus 5. Okay? You might have to make it to negative if you want it to be -5. Okay? But then whenever you hit the equals button, it's going to show you what that number is. And that's a really good way of double checking yourself. Practice using your calculator like this, where you can double check yourself and make sure you are moving the decimal place to the correct direction and representing it properly with either a positive or negative exponent. Okay, so that's just my suggestion. Take it or leave it, but make sure you either use the EE button or you use parentheses properly. If you use parentheses properly, then you can use that 10 to the x button, and that's perfectly acceptable. Okay. Additionally, so this is kind of the example of what it'll look like if you use the 10 to the x button. Okay, I don't recommend using that. Okay. All right, so let's look more specifically at positive exponential notation. So I mentioned before that positive number is represented by 10 to the 6th. So what about 3.4 times 10 to the 6th? What does that literally mean? It means you replace that 1 by a 3.4. Okay. You're moving the decimal point to the right because you've got 3.4 10 to the 6th. So when you have 3.4 times 10 to the 6th, what that literally means is 3.4 times 10 times 10 times 10 times 10 times 10 times 10 to give you 3,400,000. Okay? So whenever you move the decimal to the right, you're making the number a lot bigger. So it's got to be a positive exponent. Okay? Negative exponents are the opposite. Remember that say 7 to the -1, that number is the same thing as 1 over 7. So whenever you've got 10 to the -6, what you've got is 1 over 1 million, or 1 over 10 times 10 times 10 times 10 times 10 times 10. Okay? So then when you have 2.8 times 10 to the -5, that's the same thing as saying 2.8 divided by 100,000 on the bottom. Okay? Or 0.000028. Okay? So that's literally the mathematics that's happening whenever you've got your exponential notation. Okay? Remember, negative exponents correspond to small numbers. Positive exponents correspond to big numbers. So thinking back at our YouTube video, that's why whenever we looked at the scale of the universe, if it was 10 to a positive number, we were zooming out and looking at galaxies. When it was 10 to a negative number, we were zooming in and looking at DNA, cells, atoms. Okay? So here's kind of a summary slide that recaps. If you've got a large positive number that is greater than 1, then you're going to have a positive number here and a positive number for your exponent. When you have a small positive number, okay, you're still going to have a positive number here, but you're going to have a negative notation. Okay? When you have a large negative number, your negative sign here goes in front, but it's really, really large, so you still get a positive number. Okay? And when it's a small negative, your negative number goes here, and it's small, so the negative is the exponent. Okay? Your turn. Go ahead and pause the video at this point and practice. So what I mean by that is convert decimal notation to scientific notation. So if I were to convert 127 to scientific notation, I would go 1.27. Okay? So I now have my decimal with one number to the left of the period. Okay? It's a big number, right? It's greater than 1. So, or greater than 0. So what is it going to do? Is it going to be big? Is it going to be small? Moving that decimal 1 to the left, and it's a big number. So 1.27 times 10 to the 2nd. Okay? Pause the video, finish filling this out, and then come back to it. I'm going to go ahead and solve these for you now. All right. So in this case, move that decimal 1, 2 to the right. 9.07 times 10. Is it going to be positive or negative? We moved it to the right. Negative to the -2. What about this? 5.06 times 10 to the minus 4. Notice it's a negative 4. So does that mean it's a small number or a big number? Small. So 0.0000506. We can double check ourselves. 1, 2, 3, 4. Okay? And that's what the negative corresponds to. Now 2.3 times 10 to the 12th. It's a big number, right? So 2.3. So we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Kind of ran out of room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that is my number. Okay? Notice on this one, I don't put a 0 or a decimal here. Why would it be wrong to put a decimal point right there? Why? Because it would now make all of these zeros significant. And we don't want to make those zeros significant. They weren't significant in this number, so therefore we don't include them. Okay? So make sure you do not put a decimal point at the end of that number. Okay? We want to make sure we only include what we include and nothing more. Okay? This number, 1, 2, 3. So we've got 1.72 times 10 to the positive or negative? Small number, so it must be negative. Okay? Now, 7,200. This is where we have to decide. Are all of these numbers, are all these zeros, are they significant or not? They're not significant. Okay? So that means we cannot include them in our scientific notation. Okay? So let's figure out what number it would be in first of all. 1, 2, 3, 4. Okay? So the answer is 7.2 times 10 to the, is it positive or negative? Positive, times 10 to the 4th. Okay? Note if I had written 7.2000 times 10 to the 4th, that would be wrong. Because in this number you have 5 sig figs, and in this number you only have 2. And you want your number of sig figs to match the number that you started with, which is 2. Okay? Let's do these last ones. 1.1 times 10 to the minus 9. 0.1, 2, 3, 4, 5, 6, 7, 8, 1, 1. Double check ourselves. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And the last one, 0.1, 2, 3, 4, 5. Double check ourselves. 1, 2, 3, 4, 5, 6. Okay? Good. You can pretty much just lay out and make up numbers and just practice, making sure that you're moving the decimal the correct direction, and also making sure that you're maintaining significant figures from what we talked about last time. Okay. Oh, I forgot I had these in there. Sorry about that. All right. So remember that these scientific prefixes correspond to the number of zeros. All right. So our whole point of figuring out scientific notation is to allow us to utilize these metric prefixes. All right. So over here in the bottom left-hand corner, we can see these numbers. What you do is you want to convert them into a metric prefix, meaning whenever we have 5.78 times 10 to the 6th, replace this 10 to the 6th with a metric prefix. So let's replace it. Which one do we want to replace it with? 10 to the 6th, mega. Okay, so we want to replace it here. So that's how we end up with 5.78 megameters. And notice the symbols that are right here. Okay, your turn. Give it a try. 3.21 times 10 to the minus 3. Replace that here. Okay, 10 to the minus 9. 10 to the 3rd. Okay, so if we advance this slide, we've got 3.21, the 10 to the minus 3 is a milli. Check. 8.6, 10 to the minus 9 is the same thing as a nano. Check. And 10.0 kilo. And notice we did keep that 0 because we kept it over here. And so the 10 to the 3rd is the same thing as a kilo. Okay? Good. So notice that you can replace these at will. Anytime you see a milli, you can immediately replace it with 10 to the minus 3. Or you could immediately replace it with 0.001, whichever you choose. Okay? So notice that these prefixes are interchangeable. Okay? They go back and forth. You can use them at will and just replace. Anytime you see 10 to the minus 3, you can insert an M for milli. Anytime you see 10 to the minus 9, you can immediately add an N for nano. Anytime you see a K, you can replace it with 10 to the third. Okay? So just think about how you can replace these prefixes and use it in your everyday language. All right. So kind of to recap, metric prefixes represent the magnitude of the measurement. So you're trying to say, is it a positive exponent? It's really big. If it's a negative exponent, really small. Okay? Scientific notation can be used to represent really small or really large measurements. Scientific notation also only shows numbers that are significant. So if you include numbers that are not significant in writing out your number, it's wrong.